All right, guys and gals, this is Hess Laws, and it's not phase change calculations. It's Hess Laws and standard heat of formation calculations. So that's this one. So go ahead, I'm going to put it in slideshow, and here we go. And next one. Maybe. Someday. Any day. Oh, no. I'm pinwheeling. There we go. All right, Hess's law. So Hess law is called the heat of summation. You need to know the difference between heat of summation and standard heat of formation. Okay. So what that's saying is I am going to add up the heat, okay, in 2 or more steps, or the enthalpy change in 2 or more steps. And the overall equation, the total, is going to give you the sum of your enthalpy changes throughout the process. Okay. So here's what it's saying. A yields B plus C gives you delta H or whatever that reaction is. And B plus C yields D is give you the delta H of the next reaction. Then I'm going to add them together. Okay, A through D gives me the delta H of question mark. Okay, and remember we use Hess's law when I'm forming from graphite from a diamond. It's going to take millions of years. I can't wait that long. Can't do that process in a lab. For whatever reason, I don't have the chemicals, etc. I can't find it on the internet. So we have these values in order to find what we're looking for. Oh, there's my pretty little delta H is equal to X plus Y. Okay. All right, you're going to determine the heat of the reaction for the following equation. Oh, I'm sorry. This is kind of cut off. But anyway, you can see that it's kilojoules. So use these 3 particular equations, and I want you to go ahead, stop the recording, and find what your delta H is for the top equation up there. Okay, so stop the recording, and I'll meet you on the next slide. Oh, consult your neighbor if necessary. Well, you might not be working with your neighbor tonight, while you're watching this video, but if so. Okay, so remember here, our goal is to find the delta H of the above equation. So I need reactant 1 plus reactant 2 to be on the left-hand side. So let's look at the first equation. So reactant 1's on the left-hand side. That's good. The second equation, product 1 is on the left-hand side, so that's not good. So we definitely have to flip 2. And then let's look at 3. Reactant 2 is on the right-hand side. So the only one we're going to have to flip is equation 2. Let's see if it shows me that. All right. So this one we're good. 3 we're good. And then 2 we revised. Okay, so when I flip it, my 2CO2 plus 3H2O goes on my reactant side, and that leaves me with C2H6 on my product side. So here's what we can do. Let's see if it shows me the whole cancel. Oh, yeah, good. Okay, so 2CO2. Oh, I don't think I have these over the right thing, but 2CO2 and 2CO2 cancel. Okay, 3H2O. All right, so those 2. Here, let me just pull them all down, and then I'll go over it. Okay, so 2CO2, 2CO2 cancel. I have 2H2O and this H2O cancel to make a 3H2O on this side. Okay, I won't necessarily give you something as complicated as this, but you can see those add together. Okay, and then 3 O2s is 6 plus 1/2 gives me 7 O2s, so those cancel. So now I'm left with what I want. And don't forget, when I rearrange this, my delta H is now positive. And when I add them together, I get my new equation. My delta H is now negative 137 kilojoules, so it's exothermic. So if I were actually to write the heat, I would add the heat to the product side. Okay. So I'm only giving you one of these just to practice. If you need more problems, there's a tutorial under links, and there's practice problems under links. Okay. All right, so standard enthalpies of formation, standard heat of formation. So what it says is the enthalpy of a reaction is equal to the total formation of energy of the products minus the reactants. Okay, so delta H of the reaction is equal to H of products minus H of reactants, or H final minus H initial, whichever way you want to look at it. Okay, and it's that little crazy E sign means sum. Hopefully you guys know that by now from math or Excel. Okay, so sum of the products minus the sum of the reactants. Oh, that's what it tells you. M and N are coefficients of the substance. Okay. All right, so a problem to consider. Large quantities of ammonia are used to prepare nitric acid according to the following equation. Okay, so don't forget here, I don't have a 1-to-1 mole rate ratio of each one of my substances. So the value that you will get on that table is only going to be for 1 mole of that substance. So you have to multiply it by 4, 5, 4, 6. It just depends on whether it's a 0 value or not. Okay, so I want you to standard enthalpy change for this reaction. Here, I'll go ahead. I don't think, if you're in your book, let's see if I can go ahead and put there. So go ahead and do that for you. Okay, so go ahead and stop the recording and figure it out, because I don't know if you have a table at home. All right, so remember, I can calculate the total delta H of my reaction by subtracting the values of my reactants from my products. So first thing I'm going to do is sum these all together. Then I'm going to subtract my reactants from my products. Okay. All right. So my delta H of my reaction is negative 906 kilojoules. And if I actually, let's see, can I go back to that? Okay, so here on this problem, negative 906 kilojoules is going to go right next to my products, so plus heat. Okay, so you know that, because heat's being released. So be careful with your arithmetic signs, because they're likely a source of making mistakes. All right, that is these two things, Hess's law and law of heat of formation. Okay, so I'm going to do another one on the Q is equal to MCT with the whole chart thing, so that makes sense to you.